Okay, hi guys. So we'll be extending the Bohr atomic model for hydrogen atom. So let's do all the calculation for the hydrogen atom. Okay. So first we'll be calculating the total energy associated with the K shell. Okay. So total energy of hydrogen for associated with K shell. This would be nothing but, again I hope you remember the formula of current total energy, which is nothing but minus 13.6 Z square upon N square electron volt per atom. Electron volt. Okay, so with K shell would be obviously Z for H would be 1 and K shell is N for K shell is already 1, so total energy would be minus 13.6 electron volt. Second is total energy associated with L shell. So for L shell N is 2, so 13.6 upon 4, which would be nothing but minus 3.4 electron volt. So next we have total energy associated with M shell. So for M shell, again put N equals to 3, so you will get total energy equals to minus 13.6 upon 9, so it would be minus 1.51 electron volt per atom. So I missed the term per atom, I can just write it. Okay, fourth is, again you have to calculate total energy associated with N shell. It would be minus 13.6 over 4 square, which is 16, which will give us 0.85 electron volt per atom. Okay, so what is the energy required to jump from first orbit to second orbit? So energy required would be E2 minus E1. Energy for second orbit would be, or M shell would be minus 13.4 electron volt minus what is the energy for first shell would be minus 13.6, so the energy required would be 10.2 electron volt per atom. Okay, what is this delta E1? What is the energy required to jump from E2 to E3? It would be minus 1.51 minus 3.4. okay, so this would come out to be 1.89 electron volt per atom. Okay, next let us calculate the delta E3 required to jump from third shell to fourth shell. That would be minus 0.85 minus 1.51. that should come out to be 0.66 electron volt per atom. Okay, so just a small observation to make here is, as energy shell difference decreases, so rather energy shell difference decreases as N increases. Okay, so E decreases as N increases. Okay, so now let's suppose we have a positive charge here, and what is the energy required to bring this electron from infinity to a distance r? Okay, so at infinity, electrostatic force of attraction between the nucleus and the electron here would be 0. Okay, between electron and nucleus would be 0, and energy here would be, there would be some energy obviously here. Okay, so energy between, or rather at position r minus at position infinity, at position infinity would be minus w. Okay, so work has to be done upon the electron to bring it from infinity to here. Okay, obviously this would have a mod value and would incur some substantial positive energy to be given to this electron to bring it from infinity to a position r. Okay, so this is obviously 0, and EPR would be nothing but minus kz e square upon r. Okay, so we would require this much an amount of energy for an electron to bring it from infinity and put it in the orbit of a nucleus or a atom. Okay, so as r increases, potential energy also increases, and as r decreases, potential energy also decreases. Okay, and minimum energy will be in k shell. Okay, hence as r decreases, p also decreases, and maximum energy would be at r equals to infinity. Okay, so with this we come to an end of this lecture. In the next lecture we'll be seeing more transition of electrons from one orbit to another orbit.